Hello, very warm greeting to one and all joining us today. Myself, Lalit Shukla, in the capacity of host and convener of this uh, Frontiers of Physics lecture series, welcome you in the first lecture of this series. This lecture series is jointly organized by Faculty of Physical Sciences, Institute of Natural Sciences and Humanities, Shri Ramswaroop Memorial University, and Physical Sciences Consultorium. This lecture series aims to reach young students to give them exposure about the fields and facilitate interaction with experts working on the frontiers of the fields. Faculty of Physical Sciences, Sri Ramswaroop Memorial University was founded in the year 2012 with the foundation of university. Presently, we are running undergraduate, postgraduate, and doctoral programs in the department. And our organizing partner, Physical Sciences Consultorium, is a consortium of experienced professionals to offer our expertise to educational institutions, industrial organizations, and newcomers to uh, for building collaborations and mitigating confusion among newcomers. With this brief introduction of organizing uh, bodies of this lecture series, I would like to start with this uh, lecture series with the chairman of this lecture series, Professor B.M. Dixit sir. He's live with us this program, and we will be Professor Dixit is Professor of Physics and Director of Institute of Natural Sciences and Humanities at Shri Ramswaroop Memorial University. Uh, I'm deeply honored by your presence here, sir, and it is, your support and guidance is the lifeline for such initiatives. I would like to request you for an inaugural address to this first session of this lecture series. So please uh, say a few words in as a welcome
Thank
address.
you. Thank you. Thank you, Lalit. Am I audible now?
Yes, sir. Yes, sir. I can hear you.
Yeah. First, I would like to congratulate the Department of our Physical Sciences and specifically Dean Professor Dr. R.G. Singh and Lalit, who is basically the fulcrum of all these events. Association with our Physical Science Consultorium is also a very exciting thing for all of us because last year also we have undergone a very interesting series of lectures by some really outstanding speakers, very young speakers who really inspires the young generation on our solar system. And there we have undergone some really very exciting lectures. In the same line, this year again we plan to have such a meeting, and you see, these days we know that science requires some kind of an what we can say, it has to branch out towards some other disciplines also. And today, in terms of Dr. Abhishek, we are going to witness such a branch out of physics, who has entered himself into a very, in one sense, it is not very forte of a physicist, but I know personally many of these people who have gone from this high energy physics, nuclear physics side towards the financial forecasting sectors and done really remarkable work there. And in that line, I also wish Abhishek to have a very exciting and purposeful, prospective future to come. And with his lecture, what I am more excited is that at least we should start looking into that how the ideas of physics will help in taking decisions. It is basically making you to take a good decision while dealing with very important in these days. Probably finance is the most important thing by which we all are governed. Yes, technology is driving us very importantly, but even to drive technology you require some real good financial management systems. So in that direction, your talk will certainly enthralls us, and all my young students will start seeing it as one of the prospective career also from your experience. Though I know that switching over from pure science to finance requires one set of experience in one area at least up to a very high level, and that after acquiring that only one can switch over. But still this type of meetings will certainly give us a great platform to understand, to learn that what all things can be offered under a very, you say, structured form of physics. We can reach up out to so many other domains, and one such speaker is with us, Dr. Abhishek. I am welcoming you, and I am eagerly waiting to see the first few slides so that at least gives us an idea that where we are going to have for next 40-45 minutes. Thank you, Lalit, for arranging this meeting. Thank you, Abhishek, for joining us, taking out some time from your busy schedule, and Dean, our RG Singh sir, for encouraging such an event, and all my colleagues of physics department, my dear students. We are going to witness some really good lectures in this series. With these words, I'm stopping over here, and I'm handing over the scenario to Lalit again. Thank you, Lalit. Thank you, Abhishek, Dr. Abhishek, for your kind consent for appearing with us and sharing this dais. Thank you very much.
Thank you so much, sir. Thank you so much for your encouragement, and these encouraging remarks and guidance is certainly a lifeline for such initiatives. And now, to proceed further, I would like to invite Dean, Faculty of Physical Sciences, Dr. R.G. Singh sir, for his welcome remarks.
Okay, thank you, Lalit, and I'm also welcoming Dr. Abhishek for this very first talk. And this is definitely, as Dichis mentioned, this is really a very interesting topic, and that will explore the role of physics, principle of physics in the finance. Well, we know that I think we all can agree with this statement. The mathematics is a very crucial science in the analysis of financial issues or economics. But when you in the first view, it seems that physics and finance are like two different subjects. But if you think critically, I think you can see that both these branches are dealing with some kind of dynamical situations. As in physics, we have some kind of system which is influenced by some very crucial parameters, and a small change in those parameters leads to non-linearity and chaotic like behavior. And you can see that a small good news or a rumor can create drastic fluctuations in uh, the market and the parameters. We can see it in news. So I think uh, we can we can relate both these kind of phenomena somehow. Well, in this talk, our main audience is हमारे student हैं. And definitely they will see some good example and the known concept of physics and how those known concept of physics are related with the financial or economical kind of application. And I am sure this will deepen their understanding about the physics and economics, and the student and other audience will see how we can think about critically about a subject with a different angle, and then we get something out of the box kind of thing. So I again welcome Dr. Abhishek for this talk, and Lalit, I think we should proceed for this talk. Thank you.
Thank you so much, sir, for your encouraging remarks and guidance. So now, to proceed further, I would like to again uh, welcome our guest speaker for today's talk. So it is a great pleasure for me to introduce you on this platform. And thank you so much, Abhishek, for taking time from your schedule to be with us here at this time. And I'm sure uh, such meetings will really help our students to see the different frontiers and different fields where they can think of to make some impacts in future. So, with a brief introduction of our speaker, Dr. Abhishek Atreya, he did his master's in physics from University of Delhi in 2006, and then he moved to Institute of Physics, Bhubaneswar, for his doctoral work in the field of high energy physics. And after that, he was awarded several research fellowships, like some of that D.S. Kothari Fellowship and uh, National Postdoctoral Fellowship. And he worked in different prestigious research institutions in India. Some of them is Physical Research Laboratory, where I met him for a brief period of time. And other than that, he worked at the Bose Institute in Kolkata, Institute of Plasma Research, Gandhinagar. So, and he has presented his research work and published his research work in different national and international forums. And to pursue his interest, he moved to industry of this the way we are. He's here with us to talk about how finance is what physicists are doing in finance. So this is the motive for today's discussion. And currently he's associated with Deutsche Bank. Uh, and before that he was working with uh, Daulat Capital as a quantitative research analyst. And currently he's associated with Deutsche Bank. And with this brief introduction, I would like to invite Dr. Abhishek Atreya for his presentation uh, to this gathering. So, Abhishek, hand over to you. Please share your presentation.
Thanks, Lenny. Hi, Lalit. Thanks. Thanks for this nice introduction. And please let me know if you can see my screen when you can see.
Yeah, please.
Please let me know.
Yeah, I can see, and
Okay.
yes, it is there on the screen. Yes.
Okay. So uh, again, thanks, Lalit, and thanks, Chairman and Dean, for such kind words. Actually, I was very impressed with the way the Dean sir mentioned the how he talked about the fluctuations and those things affecting the financial market, and these things are important in physics also. Actually, it's along the same lines I'll be talking about. So the few parallels that we have. Oh God, my first slide has a mistake. God, my physics spelling is wrong. Okay, I'm really sorry. I should have paid a little bit more attention to such things. Uh, so first of all, let me start with a disclaimer. The opinions are my personal opinion, and it is not investment advice or an idea. They don't reflect Deutsche Bank's policy in any way. And what should you expect in this talk is that I am out to impress you all, and I am new to this field, so I have a very limited view. I consider myself as a student. I'm still learning, and my view is very limited as a student's view is. So I will not be able to give you the entire uh, holistic view, but I will try to give you the excitement, to convey you the excitement that I have felt in the last couple of years. And as I say, it's very limited in scope, but if someone decides to pursue it, like few of my friends have asked in past, I think it will give them a chance to see what kind of things one can do and where their expertise can be used. That's my main hope. So again, okay. So what I'm going to talk is not necessarily what I have done. You don't do all the things that I mean, you don't get to do all the things because you have your other responsibilities as well. But you do get a chance to learn a lot. So I will share what I have learned. Not all of it also, because the time is limited, but still. And these are the three main people we first come across. Anyone who goes in. So it's more like an advertisement that I'm putting here. These three people are very well known name in the field. James Simmons, he did his PhD from Berkeley. He is very well known for his work in mathematics as a Chern-Simons number, which is used in physics as a topological invariant in condensed matter physics, in high energy physics. And this guy was the first person who sort of broke that physicists can be useful. He started his Renaissance fund in early 80s, and it is one of the most successful funds till this time. He is now a philanthropist, and he has resigned from his position as Renaissance fund, but he still is a major stakeholder there. The another person, second person, Emmanuel Derman, he did his PhD in particle physics from Princeton, and he worked for Bell Labs. He also worked for Goldman Sachs as a uh, what you call as a model developer. So they studied the financial market and developed the models, and he did a good work. And there is a model after him, which is Derman Black toy uh, model. And now he is a professor of financial engineering in Columbia University. Another person is Jean-Philippe Pocha. He did his PhD from Paris, École Natural Science, if I'm correct, uh, if I'm pronouncing it correct, which my French is not at all worth mentioning here. He is a founder of the Capital Fund Management, which is which he founded in mid 90s, and he is a professor of physics at École Polytechnique in Paris. So he holds both the positions, and he does work which is what you would call as an econophysicist. So if you're interested, please look at these people look at their biographies to start with. Like, if something is which you find interesting they have done, or you would like to think along how they thought, and you can start by Google search. If you want to have a good reading about more like biographies of people, there are two books. One is on James Simmons' life, the man who solved the market. How this person, who was a mathematician, who started getting interested in market, and how he changed the perception that even a mathematician or a physicist can make some sense here. And then Emmanuel Derman wrote about his life as a quantitative analyst, which is we are short in terms in abbreviated form. You are called as quant. So my life as a quant is book by Emmanuel Derman about how he did. And if you want to go to the technical side, then you can look at a book by Anatoly Schmidt. He himself is a physicist, and he wrote a book which is where he talks about the similarities between the two, physics and finance. For a more technical side, I would say please look at Stochastic Calculus in Finance. It's by Steven Shreve. It's volume 2 is really technical. It's full of maths, where you actually start with probability measures and other things, and then go to stochastic calculus. It's quite technical. Volume 1 is lighter read. If you are interested in research papers, please look at arXiv, look at the website SSRM. You will find a lot of papers, research papers, where people actually do academic work and is available for you to see. If you are interested, so a model something, you would like to know a little bit about the field you are modeling. So if you are modeling finance, you would like to know a little bit about finance. So there is a very simple, accessible material from Zerodha online. So you can look at some of their modules just to get an idea of market, what it is. If you want a text which is a standard text which will introduce you through the basics like as a textbook, please look at Options, Futures and Other Derivatives by John Hull. It's a very standard text and very, very, very good, very nice and very easily. You can follow it up very easily. Okay, so with this slides that I consider as the selling points, what do we mean by mathematical finance? Where do the parallels comes in? The parallel comes in mostly the mathematics and many times the ideas. So there is a field which is known as mathematical finance, which is related to the mathematical modeling of the financial data. Now, just like we do in physics, we can have a discrete system or we can have a continuous system. And you can model both ways, and you can model both ways in finance as well. The tools are different. A discrete time analysis mostly does with time series analysis, deals with time series analysis, where you applied certain machine learning techniques. So it also connects to data science in a way. It also connects you to the physics. That can be a separate discussion if someone is available. You can find a good person who has moved from physics to data science. So there is an underlying connection between what you study in physics and what you the expertise that you have when you learn machine learning tools. So that expertise also can be used for continuous time. Stochastic dynamics is central machinery, and stochastic calculus is something that physicists do come across when they study stochastic systems. Brownian motion is one example, but you can look at turbulence, you can look at various others. So again, those tools, that the expertise that you have can be useful here. Monte Carlo simulations is something I think everyone does, because not all the solutions that, or all the problems that you have or you deal with have a solution which can be analytically obtained. So those things are very useful. Now, when you move to finance, you might be doing a number of things. You might be modeling. So what will you model? You would like to model how to price something. Okay. Or you might actually be looking at the risk assessment. How much is the risk of making a loss? How much profit one can make. Okay, so in that sense, you can get into a risk analysis, you can get into the modeling itself. You might go into asset management also. So where you will directly be talking to the clients and discussing the kind of models they are interested in and how you can come about it. So there are various fields one can go. And I'll start by simplest thing, which when we talk about finance, we look at stock price. So that is something which is the first thing that comes to your mind. Okay, so here I give you 4 plots. The first plot is 5-year variation of SBI stock at National Stock Exchange. Okay, from 2015 to 2020. And the next second one is for 6 months from November to March 2020. The third one is for 2 days, how the price changed in 2 days. And the last one is for 1 hour on March 9th. So the third one, the one which is on your left bottom, the 2-day plot is on March 8th and March 9th. And the last one, which is on your right bottom, is...
Excuse me, Abhishek. It
Yes.
seems slides are not moving up. The suggested reading slide is shown here. And you are talking
Oh.
about, I think, next slide. So maybe
Right.
there is a lag or...
So maybe I'll just stop sharing and share again. So I'll talk about it again. Maybe I'll share my screen again. Thanks for pointing it out. And I apologize for this. Can you see it now?
Yeah, it is there. Yeah. Now it is showing the slides where you're talking about.
Okay. So what I'll do is I'll whenever I change the slide, I'll ask whether if you can see it. Okay, that will be easier so that.
Okay,
you also
I'm there. If there is any lag, I will be talking. I will tell you.
Okay.
But you can always ask. Yeah.
Okay, so again, this is the 4 pictures that you see are stock price for State Bank of India. I showed this because that is the first thing which comes to your mind when you talk about finance. Stock market is the first thing that comes to your mind, and most of the time one is interested in how this stock market behaves. So here I just took State Bank of India stock for last 5 years from 2015 to 20. That is the first plot that you see. You see the second one is for 6 months. Then you have the third one on your left bottom. That is for 2 days. It's on March 8th and March 9th, how the prices were varying. Okay. The last one is only for 1 hour on March 9th. Now, what we see here, you have fluctuations at every scale, from years to months to days, even hours. And if you look at the last plot where you have it in hours, you see these red and green blocks. These blocks show you the variation within 1 minute. So even within an hour, even within 1 minute, the price moves a lot. So there are red where the price fell, there are greens where the price moved up, and below you can see these buildings. These buildings are the numbers of shares that are bought or sold, and which means that buying and selling happens at all scales. And this is something, again, it's a problem that we address in physics, where you study at fluctuations at different scales and try to ascertain the different phenomena associated with each length scales. So yes, that can give you an idea if I can view the price also as an emergent phenomenon. But this is again something I will not be talking about here, but yeah, it's a good exercise at least to think on those directions. So how the analysis that the people in the market have been doing depends on the scales at which you are looking, like we do in the physics also. So you have, for years, people look at the fundamental behavior of the firm, how the firm has financial health has been over the years. This is what is used when you look at your portfolio management, when you are interested in investing for longer times, mutual fund investments. If you're looking at days to months, people look at technical analysis, which means they would like to look at short-term patterns. Which means if I go to the previous slide, you see there is a time here from 2016 to 17, the price with some fluctuations are continuously going up. A price with some fluctuation were continuously going down. These kind of signals, they would like to find out. These are patterns, and that will be useful to decide if I want to get into a position or whether I want to exit my position. If I want to buy, if I want to sell. Okay. And when I enter and when I exit my position. Then, as I said, you have within the day, there are patterns within minutes and seconds. Now, you cannot possibly deal with such short terms manually. You cannot call your agent and say, buy me this many shares within 1 second. So you have to go for what you call as algorithmic trading. So you need to develop models. That's what the firms also do. So for intraday trading, when you are looking at extremely short-term patterns, you are looking at a completely different system. And your approach to deal with the system is also very different. I don't have to say that this is what we do in physics also, but since the talk is about the parallels, this is one of the simplest things that first you see. And this gives you a thought, can I use the idea of statistical physics and apply them in finance? So we have molecules which we look at, okay? And those gas molecules have a random velocity distribution, they have random positions. Can we talk something like that in stock market as well? If you have an ensemble, we are not interested in the property or the velocity of a single molecule. We are interested in the average behavior. What is the average velocity, right? Or the average energy. What should we talk about if we can talk about an ensemble? What should we talk about the corresponding thing in the stock market? And then finally, even if you start this thing, in each of the state in the ensemble, so you have each molecule which is in a given state, which has a given X, given V, you assign a probability to it. And that probability distribution you know. Can you do something like that for stock market? Let's start with this. And that would be one of the first thing to look at. Okay. Before I start, I'd like to give you even more something, more radical ideas. We just looked at the fluctuations from seconds and minutes to years. Fluctuations at all scales. In physical systems, this is related to what you call as the critical phenomena, which is when you have phase transitions. So near the transition point, like water to steam transition, the bubbles will start forming, and you will have bubbles which are very small, you will have bubbles which are very large. The entire system size. You have these fluctuations available. When you look at the magnetic phase transition, then near the Curie temperature, you have the fluctuations again available in your system at all length scales, from the smallest scale to the size of the system itself. And we saw that these fluctuations are visible in the markets from seconds to years. Can we talk something about this? The answer is yes. It's a very recent paper. The date is December 15, and one of my friends forwarded it just when I was making this talk. I thought that it will be just to maybe give your brain a little bit of exercise, present it here. And the title is also very provocative: Financial Markets and Phase Transition Between Water and Steam. The important points I just highlighted here in this snapshot. So we are looking at the ensemble when we talked about what they say the shears are models by the gas molecules. Okay. And then they study this phase transition. They extract the critical exponents, which is deciding the correlations in my system in the analogy with the second order phase transition. Well, water to steam is a first order phase transition, but they found a second order phase transition here. And a network dimension 3, fractals are another thing that we come across in physics. We come across in networks when we study networks, which is again a rage in data science. So they found a fractal dimensions of 3, and they also find the correlation time. And they also say in the end that you need to extend this model. It is a very simplistic analysis. But the point is, those ideas can be applied here, and maybe some interesting features you can try to understand. But let's go back to the first thing that we talked about: statistical physics and finance. So the randomness which is there in my statistical system, we model it somehow. We say my molecules are undergoing a Brownian motion, a random motion. Can we do something like this here? We have the price variations, they have a trend, they might go in one direction for some time, but then you don't know when they will flip the direction. So you have these random fluctuations as well. So let's try to model it as a coin toss. It's the simplest. So you have a price S0, you flip it, you get a head, it goes up by a factor U, and then it gets a tail. Okay, again, second mistake. It should be tails, not heads. So you get a tail and you have a price going down by D. Just note one thing, I've not written S0 plus U or S0 minus D. Okay, because D, if it is a random thing, it could be a large number, and that can try to take your stock price to negative. You know that the lower bound for the price is 0. Okay, it's not that it can go to negative. So that's why the multiplicative factor. And so this is your intuitive understanding of the system, which tells you that you cannot add a random variable, you have to multiply it by that factor. Okay, an important thing another is that U and D, they are not same. It's not guaranteed that the price will go up by the same amount as it will fall. हो सकता है double हो जाए, हो सकता है आधा हो जाए. They're not the same numbers. Okay, so you can now repeat this. From S1, you can take another direction and you can go, and similarly you can take it down to n times, and you can see all the possible combinations that are coming. Can we give a probability to it? Yes, definitely we can. We know the probability of a coin toss. If it's a fair toss, half up, half down. So heads, probability of heads is half. Probability of 2 heads, again we know. Okay, so you have 4 possible outcomes. Heads, 1 out of 4. Heads and tails, that is 2 out of 4. Now, whichever is first, whichever is second, that will take you to a conditional probability. I'm not talking about that. That conditional that you have a head first, whether you will get a tail, that's a separate problem. But if you just want 1 head and 1 tail, not worried about the order, you have 2 out of 4. And similarly, you can assign these probabilities. So it seems like maybe those ideas can be applied here. I have a system, I can model the randomness, maybe by a simple coin toss, and I can give a probabilities. And once I can give a probabilities, maybe I can calculate an average and see what is the average price in future, and accordingly I would see if I want to buy it or if I want to sell it. Okay. This is actually a real model which is called a binomial model, and we'll look at it in more detail. But before that, I would just look at the system again, which we are trying to model. We are looking at financial systems, and I will be talking about in this talk is something what we call as financial derivatives. Now, these are not mathematical derivatives where you take del by del p or del by del x. No. Derivatives means that it is derived from something. So a financial derivative derives its value from something else. So a derivative on a stock will derive its value from how the stock is behaving. What is the value of the stock? Okay. You can have a derivative on maybe oil, which is a commodity, or you may have a derivative on what is going to be the exchange rate in the Indian rupees and US dollars, or you may have a derivative on the interest rates, that what is going to be the interest rates in the next coming cycle when RBI is announcing the next policy. So those are the derivatives. They will have some underlying process on which it will be based on. So we need to understand those processes and also understand what is the value of those derivatives. And the most common derivatives are futures, options, swaps. These are the most commonly traded derivatives, and they are traded on stocks, currencies, as I said, USD or Indian rupees, commodities like oil, bonds, foreign exchange, interest rates, you name it. Okay, even energy or climate. Recently, people have started talking about derivatives on energy and climate as well. What does it mean? It essentially means that I'm getting into a contract with the other party. And the nature of the contract defines whether it is a future, whether it is an option, whether it is a swap. Swap is simple. We are swapping something. I'm giving you something, in exchange you give me something else. That's a swap. Okay. Future, there is a date in future where we will talk about what we have to give, what we have to take. Option, it gives you an option. It's my wish. If I want to take it, if I don't want to take it, I will not take it. Very simple. But when you start pricing them, they're not so simple. So let me give you a bit mathematical example of it. First, futures. The figure on the top that you see two long and short. So long means you own it, you bought it. Short means you have sold it. Now you have less amount of it. This is a standard language which is used in finance, long and short. Now, what is the idea? The idea is in futures that I will buy at some time t in future this stock at this price. I am deciding the price. I'm getting into a contract at this price, I will say. So let's call that strike price K. We have come to a conclusion. Okay, I will buy it at K when the stock price, and the payoff will be S minus K. If the price goes higher, I'm getting it at cheaper price K. So my profit is S minus K. So you see this green line. If the price of that stock is smaller on that particular day or less, then, well, actually if this contract was not there, I will go in the market and buy it at a cheaper price. I'm making a loss. So you see this red line here, negative. And it's a straight line. So these are called linear payoff. If the price goes up, it will pay higher. The price goes down, you will be in loss. Okay. Now, similar thing for the selling. But selling, things will be different. You will be making a profit if the price goes down, and you will be making a loss if the price goes up. So the features change. Let's look at what is option, as I said. So you get into a contract with the counterparty, and you can say, I will buy or I will sell, like you were doing in futures. But in futures, you have to definitely buy it. In options, you can say, I don't buy it. That's an option available to you. Or I don't sell it. Okay. So in financial term, if you want to get into a contract to buy, it is called call. Or you want to get into a contract, it's a put to sell. And you can get into a contract to buy. You can long it or short it. Similarly, you can do for the put also. How would the payoff look like? You will buy only if you see some profit, right? If you are making a future, like in futures, you see this red line. If you are making a loss, will you buy it? You say, नहीं नहीं, इससे सस्ता तो मुझे market में मिल जाएगा. Why will I buy it from you? Right? So that means you will not get into a contract. You will not exercise your right. So this red line will not be there. You'll just get a flat line here. And this is what you have a call. A flat line. And then the price starts to increase because the price has moved up. S is now larger than the strike that you talked about. And the higher the price goes up, the better is your payoff. Now the person who is selling it, he will be making loss. Then you are going to make the profit. So his payoff will be different. There are two parties, remember? There are two parties in the contract. And that is, you need to price it properly. And that also is important in risk management. How much is the risk? The price will go down. How much is the risk? The price will go up. And how much is the risk that I'm taking? How much money I can lose? How much money I can make? That is your risk analysis. But first you have to fix the price on which you have to get into the trade. Okay, यहाँ पे in this figure you can see 110, right? So they have agreed that they will get into a contract at 110 rupees. If the price is above 110, the person is interested in buying. If it is slightly lower, the person will not exercise it. Put is different. You can see the payoff K minus S or 0 maximum, which means I will only exercise it if the price move down. That means I think the price is going to move down. Then the stock price is low, my strike is higher, K minus S is greater, I'll make a profit. So when you go for a put, you have in mind that in future the stock price is going to go down. And that's when your payoff increases. You can see it in the figure. Long means you have bought it. Short again, the someone who is the counterparty. आपने long किया है, सामने वाले ने short किया है. That's the counterparty you have. And they will start making loss when you start making profit. This is in simplest terms, the underlying philosophy of counterparty trading. And I also give you an idea of risk. So this is also the risk. If you do risk analysis, in risk analysis, you will be dealing with counterparty risk. What is the chance that the person in front of you will default and you will lose money? सामने वाला contract को agree ही ना करे, I cannot give you the money, and defaults, then you will lose that money, right? That is a risk that you have. So that's a risk analysis, risk management problem. We are looking at the examples today where we are trying to find the correct price. What should be the correct price of this? Okay, again a provocative slide. But this I thought, because I got it a few days back in my email. One of the insurance companies sent me that if you can get into a cover with us and take this life insurance, it will give you returns at later time. Okay, and they give this very beautiful thing that you have a cover amount of 1 crore. You pay 1 lakh premium, annual premium for 5 years. So you just pay 5 lakh. You get a cover for 1 crore. You have a policy term for 40 years. Okay, and they also give this very beautiful slide. You pay from 45 to 50, 5 premiums, and from 60 onwards you start getting 10,000 rupees till 85. Okay, and then you will get the return. And when you read about what are these stars, what is this asterisk means, read the fine print. It's the maximum of 110% of the total premium minus survival benefits, comma 0. I've written it here in simple terms. 1.1 times the premium minus the benefits, comma 0. Looks like a call option, right? This first one, call option, S minus K, 0. The only problem is the K here is fixed. Benefits is something that can change over time. It's a more complicated instrument, financial instrument. It's a more complicated contract. It has a lifetime of 40 years, from 45 to 85. Okay, and you start getting money maybe 15 years after getting into the contract, from 45 to 60, 61. So it's a more complicated thing, but it is like that, similar thing. And even if you are not putting your money in stock market, I'm sure many of us are putting money in here. So maybe it's not worthless to start looking at these things. Okay. So one of the basic assumption is that you are not going to trade if you are making a loss. Lalit, please remind me if I'm running short of time. I lose track of time very easily, and I'll stop whenever you will say.
No problem. Continue. Abhi to
Okay.
it's not an hour.
Okay. Yeah, please let me know. Okay.
Yeah, sure.
So, so one of the simplest things that we have in mind is you're not going to get a trade if you're making a loss. There is a chance that you will make a loss. What about there is no chance that you will never make a loss? Oh, I will definitely trade. Okay, so that is called risk-free arbitrage. There is no risk of making a loss. I'm going to make profit 100%. And arbitrage, if I want to explain, let me explain in very simple terms. Lucknow, where Lalit is, it's very well known for chicken work, not eat edible chicken, the embroidery. It's very well known, and I'm assuming it's a slightly cheaper than what you are going to find it in Mumbai. So what a trader does, talks to some people who do this handicraft work very well, pays them a good money, gets it to Mumbai, and sells it at a higher price. Because he knows people will not travel to Lucknow to get this thing. But if I bring it and I will give a bulk order, I'll get it at a cheaper price, a discounted rate. I'll make a lot of profit if I sell it in Mumbai. This is arbitrage. You buy something here, you sell something there. In stock market, that is also done. Okay, you can buy something maybe in NSE and you can sell it in BSC. The arbitrages, they exhibit, or if they are available, they are for a very short time in such market, because now algorithmic trading is there. Computers and the orders which are flowing, they will capture these behaviors very fast and they get nullified. So on larger scales, it is a reasonable assumption that such opportunities are not there. That means you cannot make money out of nothing. As simple as that. So for example, this trader who is getting things from Lucknow, he does not have money, he has zero money. So what he does, he borrows it from a local person, pays the person in Lucknow, gets the money, sells it at a higher price, and then returns this money to the lender. Whatever that profit is, that profit he keeps in his pocket. There was no risk. This is what is called risk-free arbitrage in simplest terms. A trading strategy where you don't have money, and if you somehow get into a trade, you have zero probability of making loss, non-zero probability of making profit. This is one assumption on which most of the pricing models are there. And in the previous slide, we are looking at, let me go a few slides up. Right here, D times S0, U times S0, these numbers. As soon as you start talking about risk-free arbitrage, you realize that there is only a range in which these U and D, these numbers will rise. They cannot go beyond that. And how do you fix those numbers? You fix those numbers by trying to understand what will happen if I put my money in bank. Bank is risk-free. I put my money in bank. It's a good bank. I'm not talking about something like Yes Bank that is collapsed. No, but maybe a good bank like SBI, which is backed by government, reasonably risk-free. You have put in your money there. It is in the safe deposit or fixed deposit or whatever, and you have a return R, which is 3% or 5%, riskless. You are going to get your money 1 plus R times your principal that you have put in. So you always compare with that. Suppose your market goes down. So this factor D is larger than what you are getting in the risk-free by putting it in the bank. Which means कि worst case scenario में market गिरेगा भी तो भी I will get more money than what I am getting by putting it in the bank. Then what will you do? You will borrow money, okay, put it in the stock, okay, then you will get a return which is 1 plus R, and then pay whatever you have borrowed, and the net profit is in your pocket, right? So which tells you that D cannot be greater than 1 plus R. When the market goes down, the losses you are going to make, they will be more. Okay, that's one thing. So this is again related with the risk. And there is an upside. Now, if the market is going up and you say, "Arey yaar, itna upar gaya, but I still get more money by putting my money in the bank." That means the return in the bank is more than what I am getting by putting my money in the stock. No one is going to put their money in the stock. What will they do? I'll sell my stocks, okay? And then whatever the money I have, I will put it in the bank and I will get a return on this, which is 1 plus R. And this 1 plus R is greater than whatever the stock market will give, and I'll put the and I will have the profit, net profit available to me. What does it say? That if you have a money market available to you, okay, which is giving you a interest return R, for example, FD or something, the market, when it performs good, when it goes up, it will give you returns which are more than that. And when it will go down, when it is performing bad, the chances are that you will lose more and your returns will not be as good as what you have put in the bank. So this gives you a range in which your U and D, these two parameters will be there. The assumption is in this entire discussion that I am taking money from a money lender, okay, and I'm giving also some money somewhere. Those interest rates are same. It's a simplifying assumptions. We know these interest rates are not same. If you borrow it from someone and if it's a local person, the interest rates are sometimes really crazy. But it's a simplifying assumption like we do in physics. Take a simplifying situation and then maybe we'll make it more complicated. Okay. So now the question is, you have to set the price. What is the price today? Okay. How do I know? What should be the price? Okay. So the idea, the technique that we use is that you start with the no arbitrage assumption and you do a simple exercise which I just discussed some time back. I mean, in the previous slide only. You take some money, invest some of that money in the stock market, some of them in the bank, money market, and then, so this becomes a portfolio. Portfolio means a set of entities in two different kind of markets. And that is your entire total money invested. So you will have a return coming from stock, you will have a return coming from money, and the total return will be your total profit. It's an example of a portfolio. So you construct a portfolio. Okay. And this replication technique, that my derivative, whether it is a future or it is a call, I'm replicating it. I'm getting the same payoff as I will get by putting some money in the stock and some money in the money market. How do we do that? So chaliye, at t0 right now, I have some money, x0. I bought some delta 0 shares. So delta 0 S0 is my stock price. Delta 0 shares with S0 price. Delta 0 S0 is my total money. X0 minus delta 0 S0, it is the money I put it in the bank. Now at time t1, the coin toss came up. I get a stock price at time 1. My value becomes delta 0 S1. In the money market, I got a return 1 plus R. It is a risk-free return. I will definitely get that return. I know bank mein FD hai. I will get that return always. 1 plus R, x0 minus delta 0 S0. Okay. Now you say that this combination I have invested, it should behave just like as if I have bought a call option or I have bought a future option. Okay. So then you would say that the value of my derivative V1 at time 1, V1, it should be same as the price of my portfolio at time 1. Okay. This is a condition if you have successfully replicated it. Okay, fine. Again, the assumption. The assumption, when I say delta 0, I did not say how much you can trade. Whether you can trade one stock, you can trade half stock, you can trade 1/10 of the stock, you can trade any amount. Okay. So that is another assumption which is going in this discussion. So you will have two equations. So these two equations tells you when the price goes up, H, you get a coin toss heads. One is the equation when you will get a coin toss tail. So price is going down. And you can use these two equations, get delta 0. Okay, two unknowns. You don't know unknown how much wealth I should start with. मेरे पास अभी कितना पैसा होना चाहिए, and how much shares I should buy. Okay, so this is what you get. It's a very simple exercise you can do. So it gives you an idea how much shares I can buy and how much money I should have in my hand. So this is P delta Q delta. So these are, if you look at this, it looks a lot like the expected value, the probability of V plus Q, which is the probability of coin toss with tails. So P1 times value 1 plus P2 times value 2. This is something what you do in the expectations when you calculate the expectations. And we will revisit this discussion later on. So now you know how much value you should have in hand, how much shares you can buy. Okay? But do you still know what is the present value of the derivative? ये तो सारा discussion V1 पे है. All this discussion is happening at time T1, final time. What should be the value today? So the no arbitrage condition, which we just discussed, that there is no arbitrage available to you. That means you cannot buy from one place and sell it and other place and get a profit. If this possibility is not available, then whatever money x0 you have estimated here, it should be the price of the derivative today. And you can again try to prove this by looking at the two cases. By when you say that let us assume V0 is greater than x0, and you can also try to assume when V0 is less than x0. What will I do? If V0 is greater than x0, तो मैं derivative बेच दूंगा. I will sell the derivative and I will get a profit. If V0 is less than x0, I will do the reverse. I will sell the stock and put the money in the bank and I will get a return. This is again a situation of arbitrage, and I am assuming that there is no arbitrage. So these two situations are not available to me. What is the only situation? A function is not greater than, and then function is also not less than x0. The only thing that remains to you is it is equal to x0. So it has to be the present value of the derivative, the wealth that you started with here. ये जो हमने x0 का expression estimate किया, this should be the money in my hand. This should be the price of my call option or future or whichever derivative you are talking about today. Okay. Again, another assumption. I am not talking about here कि how much money I am giving to the broker. कि भाई मुझे पैसा दे दो. Oh, sorry. How much money you are charging for buying the stock? So there is no trading cost. I am not considering them. There is no bid-ask spread, meaning that there is always in the market, the person who is selling wants a higher price, the person who is buying wants a lower price. So there is always that difference. Okay, this is called a bid-ask spread. So we are not looking at these technicalities for the time being in this discussion. But most of the time, you know that these things can be satisfied. Yeah, how can they satisfy? Please don't ask me right now. I'll have to get into the order dynamics, and then that's a separate issue. I'm not covering it here in this talk. Okay, so the probabilities that we were talking about, again come back to this. We have those two probabilities, P delta, Q delta. You add them, you'll get 1. These are the expression which are available to you. You add them, you'll get 1. And you can interpret them as probabilities, as I said earlier. So you are actually essentially calculating the expected value, the expectation value, which we initially asked. In statistical mechanics, we are not interested in the exact price. We are looking at the expected velocity, the average energy, average velocity. In finance also, we are looking at a similar system. Okay. Important point is, the price was going up by U and going down by T. P delta and Q delta are different from that. These are risk neutral probabilities. They are not the real world probability that in reality how much the market will go down. No. They are the probabilities that if you take some money, put it in the market, then you take some money and you put it in the bank, money market, then that combination will give you a risk-free behavior, means that it will give you the same return whether the market is going up or going down. So these probabilities are different from the real probabilities. These are called risk neutral probabilities. Risk neutral probability, no arbitrage conditions, are the founding stones of pricing models in finance. I've talked about, I've given a small introduction of these systems or these concepts, sorry, uh, in terms of a discretized or a binomial model, which is the simplest model available. Later in the talk, we'll go to the continuous system. But let's just finish this discussion. Okay. Since we are talking about the risk neutral, and I said that the price, whether the market goes up or market goes down, you are going to get the return R, because that's how you constructed your portfolio. This is in financial terms called hedging. So in stock market, when people talk about stock market, they ask, are you hedged? You have bought a stock. How are you hedging it? Are you buying something else to hedge this risk? This is the simplest understanding of what you mean by hedging. There is a risk of losing money or making money in the market. You are putting a part of money here and part of money in some other trade, so that the risk in one directly cancels the risk with the other. Then you are hedged. If the prices goes up, this quantity will give me profit, this quantity will give me loss. And if the price goes down, this quantity will give me loss, this quantity will give me profit. So I have an expected value which is more or less constant. So this idea, which is used very regularly by investors, hedging. And I just give you a very small model which discusses how you can hedge and replicate a derivative. Now, let's just put these numbers, some numbers in that model which I gave you, okay? And how I can price a call option, I'll show you. So let's start that the price today is 8 rupees. And I say that I get into a contract maybe with Lalit that I will buy when the strike is 20 rupees, when the stock price is 20 or more. So this is the strike in which we got into. The probability of so if it goes, the price goes up, it goes by a factor of 2, it goes down, it goes by a factor of 2. So U is 2, B is 0.5, half. So from 8 at time 1, I have rupees 16 or rupees 4. And then if I have rupees 16, then I can get 32. If they double, market goes up, or I can get 8 rupees. Similarly, from 4, I can go to 8, or I can go to 2. And then I can go to the third time. This is my final time, expiry. After this, the contract expires. I have to make a decision now. Okay. So it's a simple 3-period model. And what is the value of the contract here? Maximum of S3 minus K. So at each of these points, I have to estimate S3 minus K. The stock price 64, price rupees K20, S3 minus K gives me 44. Here 16 minus and strike is 20, I get minus 4. So it is the maximum of minus 4 and 0, so 0. Here again, 20 is greater than 4, so 0 payoff, 0 payoff. What does this mean? In these 3 situations, I will not buy the stock. I'll say, nahi bhai, I will buy it from the market, it is cheaper there. I'm not going to buy it from you. I will buy the stock only in the first case. Okay? Because then I'm getting it at 20 rupees. In the market, the stock price is 64. I make a profit of 44. So this is the payoff I get. Because I can immediately sell it in the market at 64 rupees. I bought it at 20, immediately sold in the market. I made 44 rupees net in my pocket. Okay. So I know the value here. The aim is what is the value at T0, which is V0. Do I know this? No. So let's get back. From V3, get the value at V2. From V2, we get the value at V1. From V1, we get the value at V0. Step by step. Then I need the probabilities also. So let's see. The probabilities, let's assume half and half. The probability going up, probability going down. It's just a number I have thought of out of my hat. And you can do a reverse calculation. What should be your R? The R comes out to be 0.25. It's an illustrative example. Things might not happen like that. They will have a different P delta, Q delta. They might be 1/3 or 2/3 or something like that. Okay. It's just an illustrative example. How to calculate. Okay, fine. So you know what is the P half, Q half. So P 44 divided by 2 plus 0 by 2. That's 22. Okay. Divided by 1 plus R divided by 1.25. What value I will get? I'll get 1.76. Here I will get 0. Now I can go back, repeat the same step. Half of 1.76 divided by 1.25. 7.04, 0 here. And again do the same exercise, and I know the price today. So this is the price, 2.82 rupees is what is the price of this call option today. Okay, I give this much money and I have a contract with me which says that after 3 periods, it could be 1 month period, it could be year period, I don't know, some period. After 3 periods, I can decide whether I want to exercise this or I want to exercise or I don't want to exercise. Someone else can get into a strike with a strike of 10 rupees, they will have a different payoff. So the call price will be different, and maybe it is a good exercise. You can put K equal to 10 and try to see how the price will behave, because now here it will be 34 and here it will be 6, now 0, 0. So things will change slightly. So the price will change. So one thing that you know straight away, that the price depends on what is your future expectations. That's the contract value of the contract will depend on where you think the market will be. That's how you will estimate and come to the appropriate risk neutral price today. Okay. And this binomial model which I gave you, it's a simpler version of something what we study in finance, or you will come across if you study finance, or something called Black-Scholes Melton model. 3 people who first talked about it. So Black-Scholes published this study in 73. Melton gave a more mathematical rigorous treatment, which we'll talk about. Some of it we'll see later in the coming slides. And unfortunately, Black didn't survive till 1997, but Myron Scholes and Robert Merton, they both were there to receive their Nobel Prize for this work in 1997. And in these 25 years or so, their work became the founding stone for constructing more advanced models. And this was the first work they have done. In 1973, when you talk about, I compared it with physics, I still consider that it's a very new field. If you look at how old statistical physics is, coming from the time of Boltzmann, more than 100 years. It's a very new field where the mathematical expertise and the ideas can be used. So the thing is that we assign the probabilities in the coin toss. The distribution is what you call as the binomial model, and this expression NCK, I think everyone would have seen it, and when you look at the permutations in the combination, n factorial upon k factorial n minus k factorial. And it has k events which are true, then n minus k events are false. If you have a probability p for k events, 1 minus probability for not happening that event. So this is a simple binomial model. If you look at the continuous limit, you get two distributions. The one is what you call as a normal distribution. Okay. The plot here is of a log normal distribution. Okay. So n going to infinity, that means you have large trials and the probability remains constant, like what we study in the binomial model. Okay. In the binomial model, we studied that the probability remains constant in time. It's a constant p, but you can now take this n to infinity. You can do this infinite tosses such. You will see that your normal distribution, binomial distribution goes to a normal distribution. So if you look at the stock prices above, let me show this figure again. Please bear with me. Yes, this figure. So you see it's u times s, d times s, u square s0. You take the log of this guy. So you look at the log of s0, log of s1, log of s2. Then you see that it is s0 log s0 plus log u, log s0 plus 2 log u, log s0 plus 3 log u. Which means that if you take the logarithmic of the stock price at each time, that because the logarithmic is going as log something plus something else, which is a random variable, that can take negative values. And that is allowed. No one is stopping you, the logarithmic, to take negative values. And that distribution will be a normal distribution. So that's why it's called a log normal distribution, log normal model for stock prices, where the log of the stock prices follow a normal distribution. So that's why I wrote a function, a probability function for log of the stock prices. It follows a normal distribution. Okay. Another limit is when you take large number of trials, okay, but your probability also changes with it. So p is not constant, but n times p is constant. N changes, p decreases. This gives you a Poissonian distribution. And we have seen both these distributions when we study our PSC. Even I think in class 12th, I have seen at least the Poissonian distribution when we study the radioactive decay. Okay, you can put k equal to 1. What is the probability of having decay of one molecule? You will have your standard radioactive law decay process. So normal distributions we have seen, it's a Maxwellian distribution standard. When you look at the gases, the kind of discussions we started with, okay, the ensemble, how to define the probabilities and other things. So for a gas of molecules, this is what you will have. So these ideas are not new to you if you have had a bachelor's course in physics at least. And as we modeled by coin tosses, you model this randomness in these systems, in gas molecules, by Brownian motion. And this was the first famous work in physics was by Albert Einstein in 1905. And this is there in your, as I said, radioactive decay, gas molecules. We have just seen the example in the stock market. So I'll just spend a few minutes to understand what this, how do you define this? A Brownian motion is a continuous function. Okay, important point, I'm mentioning it is a continuous, it's not smooth, so it is not differentiable. I'm not saying anything about the differentiability. Actually, if you look at Brownian motion, it's not differentiable. It's a continuous function. It has a value at each point. It's not discontinuous. And you call this continuous function a Brownian if at time intervals t1, t2, the difference in the value and the previous values, they are all independent and they all have a normal distribution. So which means there is a range of values my process can take at time t2 because you did a coin toss. So at t1, you can go up or you can go down. Imagine a system where you can take large number of such values. So you will have a lot of values at time t2. You differentiate, you take the difference, the value which is there at t0, okay, or t1, whichever it is. Then you will get a range of values of these increments, delta w, okay, dw, or whatever you want to call it. W, the value of the function at time t2 minus the value of the function at time t1. All these increments, this set, if you look at this set of the values, they are independent and they all have a normal distribution. Each of them. You do it at each of the times, that's what you should see. Okay? If it's not a normal, it does not have a zero mean, you can always subtract the mean from the value. Okay, so you can get the expected value, the mean to be 0. The variance is the most important part. The variance of a Brownian motion increases with time. It is proportional to the time. The variance is square of your standard deviation. Okay, so if you have a distribution, you'll see that in a Brownian motion, when the gases are there, you insert gases. You might have seen those simulations or YouTube's videos. The distribution, it spreads, starts spreading. Okay, so that is what one of the main feature of the Brownian motion. The variance is directly proportional to the time. It increases with time. And you can again expand this formula for the variance. Okay, it's just x minus mean and the expectation value. And you do that, you can see that in the case of this delta t going to 0, you can show it. It's a very simple exercise that you will see that dw, which is a fractional change in a very small interval delta t going to 0, the change is dw. The dw is equal to t. Now this is a property which is unique to random processes of Brownian motion. It's not there in any other continuous functions. Specifically, it's not there in any of the differentiable functions, smooth functions. If you calculate this quantity, it will be 0. Why? I know the derivative. For a parabola, I know how the derivative behaves. So I know whether it is going to go down or whether it is going to go up. The function is going to go down or it's going to go up. It will not take a range of values at the next step. So that the technical term, the mathematical term for is the quadratic variation. The quadratic variation is non-zero for Brownian motion or in general stochastic processes. Okay, this is a very important result. It's 0 for your, so that's why stochastic differential equations, their integral cannot be done using the standard integral techniques that we study in class 11th and 12th. It's because of this property. Another example, which is a generalization of the Brownian motion, is Langevin equations. Okay. Now, Lalit, can you just tell me if everything is okay?
Yeah, it is okay, but it's like 1.5 hours. We have whatever the program is.
Right. So
try to be like
right.
10,
Wrap up in
15
10
minutes.
minutes.
Yeah,
Okay.
10, 15 minutes.
Wonderful. Okay.
Yeah.
I guess I'll not be able to show you the solution of the differential equation. I'll try to take you to the differential equations when. So okay. So we have the Brownian motion, which is the continuation, the continuous limit of when we do the coin tosses that I've tried to motivate it. The generalization of the Brownian motion, again, we study in physics, is what you call as Langevin equation, where you look at the force is proportional to the velocity plus a white noise term. That white noise is a random noise. Okay. So you have glass molecules colliding, and the force with which it collides with the other molecule is directly proportional to its velocity plus a noise term. This is an example of a stochastic differential equation. Can you write a similar equation for a stock price? The answer is yes, you can. And that is the stochastic calculus for finance to you. You have a Langevin equation, you can write a similar equation for stock price processes as well. Okay, and to make sense of this equation, you take the expectation and the variance. So this dx you write as delta x, a times delta t plus b times delta w. Okay, and then you take the average. dw and dx are in limit when t goes to 0, but if you look at when delta t is not 0, some small finite number, and you get the expectations. You know that the Brownian motion by definition has a variance 0, so the only thing which available to you is a times delta t. A is a constant. If you look at the variance of dx, the first term is a deterministic term. It will have a 0 variance. It has no variation. Second term is the one which is noise. And it will be, as you know, dw times dw is dt or delta t. So b square delta t. So this is the variance of your stock price or your stochastic process. And a times delta t is what is your expected rate. When we looked at the call option, the binomial model, and I tried to give you the call price with a simple formula. It is not the equation for the stock price I'm interested in. It is some function of the stock price I'm interested in. Okay. So I will be given the equation of the underlying stock or something else, maybe commodity or interest rate or whatever. I'll be looking some function on this because I'm doing a derivative pricing, some function of that. How does that function behave? I know from my simple calculus that df is f prime dx. It's a simple understanding which I have. And as I said, it will break in case of a stochastic process because you have this another term appearing, half f double prime, which comes specifically, if you do the derivation, specifically because you have a non-zero quadratic variation. I'm not giving you the derivations here, but if you look at the derivation, you will see that it is specifically because of this non-zero quadratic variation of the Brownian motion. You get an additional term for a Brownian motion. If it's a function of a Brownian motion and you differentiate it, there is an additional term which is not available in your standard calculus, which Newton put forward. Okay, and this was captured by very beautifully by a Japanese mathematician, Kiyoshi Ito. And this is a lemma which says that a function which is a function of a stochastic process, this is my stock price right now, function of my stock price, it will another be a stochastic process. It will be another stochastic process. It will have its own drift. It will have its own variance. Now, the drift is some derivative, partial derivative with my stock price and time, plus it has an extra term which is being contributed by this f double prime, which is coming because my Brownian motion has a non-zero variance. if I remove the Brownian motion from my equation, the red terms go to 0, and it's a simple deterministic equation. As you can directly find out that it is nothing but a chain rule that you have done. Okay, these extra terms are coming because the system has a noise, inherent randomness, stochasticity associated with it. Okay, let's look at example. I know return. I have tried to motivate that my underlying is log of s. It has a normal distribution, fine. So x is, let's just say, log of s. So then my stock price is exponential of x. What should be the distribution of my stock prices then? I can use Ethos lemma and apply it. I know there is a first term. There is no time, so this del g by del t goes to 0. You take whatever derivatives of exponential, it will again be exponential. I get a mu plus half sigma square. The variance, sigma square, and it is s square. So my equation is now not a dt plus b dw. No. It is mu s dt sigma s dw. Which means that the mean value, the expected value, is a function of time. It changes with time, which is what you call as trends. It goes up, then it trends to go down, then it tends to go up. And when it changes the direction, it's because of my second term, which is sigma s. How much it will change is also depend on what is the stock price at that time. Okay. So this is the standard model which people use, the simplest model which people use in stochastic calculus or stochastic models when they look at financial derivatives. This is called a geometric Brownian motion or log normal process, and this is what we'll be taking forward. So if you want to talk about the European options, right? So we know that it is stock price at final time minus k, the maximum value. What is the expected value? That's what. The expected value is, there is a probability distribution, which is the probability measure, which is given to me. And that probability measure is because of my underlying Brownian motion dw. Because that Brownian motion tells me what is the probability that my stock price will go somewhere else. The first term, which is u tilde minus half sigma square, which you are seeing here, it is deterministic. U is constant, sigma is constant. You can integrate it. There is no stochasticity in this. The probability, the stochastic behavior comes because of this. So in the expectations, my probability measure, it will associate it with what is my Brownian motion. Now, this kind of expectation is not something very new to anyone who has studied path integral formulation of quantum mechanics. Okay? Or advanced quantum field theory. If you have come across these terms, you see such probabilistic measure coming in there. So, but the point is, this is the real world situation. You are looking at the real world scenario, and this is not risk free. You have to look at the risk free rate. You have to come up with a risk free pricing. And for that, there is a interest rate R in the market, which is your risk free rate. I don't know how to calculate it right now, but assume that you know somehow. Okay. This is another exercise to how to estimate this risk free rate. That's an exercise in itself. But assume that you get it. Then you can take the price and discount it to the e to the power minus RT. And then you can do a simple application of Ethos lemma. Okay. And you will arrive at this equation. What you see in the brackets, theta dt plus dw. You define it as a new stochastic process. Once you define it as a new stochastic process, okay, w delta, then you see that there is no drift mu times dt associated. It's what you call a martingale. It's a proper Brownian motion available to you. Completely random. There is no trend. It has no tendency to go up or no tendency to go down. It will fluctuate around your mean 0. Okay. This is again now becoming your risk neutral system. And these two probability measures, the probability measure P, which is for the real world measure dw, and probability measure P delta, which is related to your risk neutral world d of w tilde, they're related by this transformation. And again, you have seen this in physics when you do coordinate transformations all the time, okay? But if you are doing advanced physics, quantum field theory, you will see a function, gauge fields, electromagnetic fields, you do Lorentz transformation on them. Essentially, what does it mean? You are changing your probabilities of certain paths in quantum mechanics to be taken when you do these transformations. And your probability measure or the measure of the integral changes. So it's the same ideas which are being used. So you are in some way, maybe loosely, very loosely, you can say that I'm working in a specific reference frame where my risk is 0. So I'm working in a risk-free frame of reference. Okay, I can do a coordinate transformation and I can go to another frame which will be the real world system, which is not risk-free. Okay. I think maybe I can stop here, Lalit, because it'll there are a
Yes,
few more
Abhishek,
things
yeah,
that I
yeah,
can talk.
it's
Yeah,
like
it's all
we
right.
have 1 hour and
Thank you.
40-minute session is
Uh,
almost there. So I think we should
so I'm
stop
sorry
this.
I could not.
And no,
Sorry I
that's
could not
okay.
finish
That's
it
okay.
off.
We could. It was interesting and with the flow. So it was. I hope it was engaging, and the people who are with us, and later on those who will be looking it on a YouTube channel.
Yeah.
So this will be like in
Well,
continuity. So
actually,
that is
I
why
wanted
I
to.
think okay.
So just give you a very brief thing. There is a corresponding differential equations, which was because a discussion which Feynman had with Mark Kak, who is a mathematician. So Feynman actually contributed in mathematics and stochastic calculus, which led to his name being coming up in finance again and again. And the differential equation is, you can show that the differential equation which I'm talking about here is like a heat equation. So which is again the solutions of this heat equation you know in physics very well. And this is the kind of solutions which you have in terms of Gaussian distributions of the process available to you. So finally, this is what I was coming to, but sorry I didn't do it properly. I was too
It's all right.
maybe.
It was a lot of
Thank you.
information
Thank you
and a
very
lot
much.
of new things to learn. And I'm sure that the people who are with us and later on who will be visiting our channel to look at the discussion will find a lot of interesting
Yes,
things.
please.
And
If there are questions, I mean, yeah, definitely, I'll be
yeah,
happy
so
to answer even
for
later
the
also.
we are already late and we are moving towards the large segment of this discussion. Here we will take some few selected questions for discussion, and so there are some questions I would like to take. There's one question by uh, Aditya Sarda. Can you see this on
Yes,
screen? I'm
yes,
reading it
yes.
again. If if the coin is rigged and its probability to
Yes.
get head or tail is not known, So
Yes.
then, how do you formulate stock markets can be triggered by infinite number of global possibilities? In short, so I would like to hear the comments
Right.
on that.
Thank you, Aditya. It's the first question which would be there, and thanks for asking it. We just discussed the probabilities of going up and down, which is what we call the risk neutral probabilities. P tilde, Q tilde, they are not same. Okay. They add up to one, but the probabilities of market going up and down are not same. It's there in the model. Uh, I at, I artificially choose my P tilde, Q tilde to be half, just to even convey how to calculate it. But it all depends on your R, which is your interest rate. Okay. So if your interest rates in the market are different, if you I chose it to be 0.25. If the bank is giving you at zero point 0.3, or if the bank is giving you a rate, or the money market is the risk-free rate, I'm assuming, to be maybe 0.2, your probabilities of going up and down will change. So the model already has that feature. The only thing is that you get those probabilities if you know the risk-free rate in the market properly. That is a very important point. And we know that risk does not remain constant throughout. I mean, rate does not remain constant throughout. Rates change over time. So those are other extensions of the problem, and that's how people actually do in real life. They estimate what is the interest rate, then they calculate what is the probability, and they also consider the evolution of interest rates in time. Those are different models separately. Actually, Emmanuel Derman, the person I showed in one of the first slides, he gave a model of interest rates, just like the binomial model I gave you. He talked about a model of interest rates, and he became very famous for that. And yeah, so yes, it's
Okay.
people
Okay.
do calculate such things.
Yeah. Yeah. Thank you for your comments. I hope Aditya is okay with that, and I'm moving towards the next question in the section. So there is a question: the quant finance and economic physics are two different things.
Yes,
Are they
yes.
have something in common? So your comments on that?
Yeah, they are different with some common features. So if you remember, I showed a slide which was talking about critical phenomena, okay, where it says that there is a phase transition happening in the market, possibility of phase transition. So this is the idea of physics applied to the economics. If you look at paper by Jean-Philippe Bochard, again another person I put it in one of the slides, he works on those kind of things. He actually works on systems which you can even treat as the grand canonical ensembles. So he has a system, he has mixture of them, not just one gas, he has mixture of gases, he has firms, he has families who are employed in the firms, there is an exchange of money between them, okay, and then he looks at when the firm goes, and then there is a global economy, so the energy of the global system, okay. And then he also discusses in those papers how the interaction or the exchange of the money is happening between the firms and the families. So molecules, how do they interact? And then in some of his models, he argues that there is a possibility of phase transition, which is what you call as a crisis. Suddenly the entire things goes down, some of the firms collapse. There is a so yeah. So you have economic physics, which is the idea of physics applied to economics. Yes. Quant finance is a very broad term, which says applying quantitative skills in finance. So unlike the traders are street smarts, they know, they have the expectation, they have the experience. But can you model it? So data analysis, for example, if you do, you take a lot of data and try to get certain features out of it. You try to fit a curve. You look at the distribution. These are quantitative skills that you are trying to see. So quant finance is a broader term. Econophysics, I would say, is a subset of that, in my opinion. I mean, I
Okay.
might be wrong if someone has
Yeah,
some other opinion.
Thank you for the comments. So, since we are already running sort of time, so I would just like to uh, ask you one question, and then we will wind up the discussion. That the students which we are part of our department, undergraduate student from physics, and those are later on or joining us or listening. So, if somebody who's interested or find these fields are fascinating, so how they can make career in that field, and what could be the crunch points where they should be focusing for. So something like since you are in the field and know people who are working doing things, so like your comments on that, somebody who is fascinated or feeling interested about the fields. So how the people from physics background or undergraduate students in physics stream can make career there, and what are the career options and opportunities?
To be very honest, undergraduate, I mean, someone who has done just BSc, uh, I mean, getting a higher position is very difficult. Or even to start a career in a good place is very difficult. Generally, because if you are going for quantitative fields, people are biased towards engineering sciences. That's a general bias we have. But yes, if you are masters, I
Yeah,
have
means like
if
somebody
you are
who is
masters,
interested, how to be
yeah.
their interest. Like if they are doing a research, then theoretical physics or high energy physics, like you
Oh,
did your
actually,
PhD in high energy physics.
right.
So the kind of move they should make in their career,
No,
which
I
can
even for someone who is doing BSc, I have some advice. You see, uh, in your during your coursework, you do study a lot of things like heat equations and other things. And I just gave you an example. I could not come to the last slide, but heat equations is one of the equations which we use in a different name, Black-Scholes equation. Okay, and solve it. Those those knowledge, that idea that you have is very helpful. So please read it. Please go through those topics very carefully. You, in your real analysis, you talk about linear algebra, extensively used in data analysis, extensively used in field of finance. Okay, because you talk about always matrices, you always talk about correlations, then you have a correlation matrix, you diagonalize the matrix to make them independent, you find the basis vectors and all other things that you do. When you do all this analysis, this is this is a part of what people do in finance also. Okay, so at least you know how to do those things. You might not be an expert on this, but please pay attention to those which you might think ki kya nonsense here. Where will we use it? They have application in real world as well. People who have done masters, they will have more technical advantage, and PhDs definitely. You, you learn something in PhD which you never learn anywhere, which is how to think, how to approach a problem that you have never faced before. And this is what people value. And moreover, when you are doing PhD and when you finish your PhD, if you do a decent job in your PhD time, you know that what you are going to do is only because you have to do it. So no one has to come and push you to do that job. And all the skill that you have acquired, how to solve differential equations, how to uh, work with stochastic processes. Even if you have never worked with stochastic processes, I did my PhD in cosmology and high energy physics. I never worked with stochastic processes before. I can read and pick it up. That confidence I have. They also have that. Because this guy has worked and looked at research papers which are of different types, understood them. That training which you get during your PhD is your biggest support. Plus, you are mathematically skilled. Okay. Sometimes one of the biggest thing is because you give so many talks in various places, you have a decent communication skills as well. And that communication skill is very important because you have done something and you want to now convey it to your manager or maybe to your team members or someone else. You get communication skills, you get mathematical skills, you get independence, which is very much valued here. You are not dependent on any other team members. Okay. You are hardworking simply because you know that your life depends on it. That's how you do your PhD. यार नहीं करेंगे तो फिर क्या मिलेगा? ये तो करना ही है. It's not my guide's job to finish my PhD. It's my job to finish my PhD. Normally, you come up with that attitude. If you can take even half of it, I think you'll do a very decent job. Because in at least in India, the background people, mostly people are coming from engineering and management courses, which is a very different training. If you look at John Hull's book, the mathematics there is reasonably simple. A person who is doing MSc can solve each of these problems very easily and understand it. Okay. The challenge is when you go from John Hull to stochastic calculus of Shrev, which a physicist is in a very good position to understand and implement. Unfortunately, I could not go to that level of advanced mathematics. I was going towards it, but I realized the time is getting over. But the entire training of 8 to 9 years, which you get in BSc, MSc, or maybe few years in PhD, it makes you someone whose value you might not have in academia, because it's like first among equals. सबका level एक है, उसमें से सबसे अच्छे को value मिलेगा. But as soon as you go in industry, you realize, oh my God, there were so many of them like me that I did not consider myself worth. But maybe I'm not that useless as I'm considered. So that's a very good feeling you get. So
Yeah. So thank you so much for this motivation and the way the people who are young students who are going to pursue higher education and research and all. So
yeah,
I
please do
hope
at
that
least
this really
masters
gets
if you want to have.
Yeah,
I have
yeah.
many friends who have moved not only to finance. A friend of mine has gone into automotive industry. A friend of mine is in Infosys or some other place. But there is a masters gives you a technical expertise to some level, and please do justice with your coursework. Forget about whatever you will learn extra.
Yeah.
That is a separate thing. Plus, please do justice to that.
Yeah, so that is
I
like
don't know.
for our students who are joined with us.
I felt,
So
yeah,
for
I felt
them,
like
it is something interesting that they should understand that higher education, pursuing higher education is
it's very,
a
very
very
useful.
value-adding thing. It will add
Yes,
values to you. It will give you
yes,
skills which can be useful in different
yes,
fields, not
yes,
only in
yes.
physics. Like
Not
something
only in
which you're
physics.
learning, it's like you have to do that only. It's like there are different fields open for you. Just you need to get the skills and
If you do
focus on
if
it.
you do
Yeah.
MSc physics, sorry Lalit, if you do MSc physics, you have a mathematical physics course. You learn
Yeah.
half of the calculations that I'm going to do, or I have shown you. You do them by hand. Okay,
Yeah. Yeah.
you know how to do them already. So when you see them, you are not scared of it. You do quantum mechanics course and you do real analysis, real algebra. You have done 90% of the problems, or at least seen them properly. You're not scared
Yeah.
of it.
Yeah.
That
So
skill
that is
is
like
unmatched. Yeah.
advice for students in our department, like to pursue a higher
Yeah, please.
education, and you will
Yes.
add values and skills that will be useful for
Yeah. To your portfolio.
different.
Yes.
So the, with that, it's about 2 hours since we have started, and I think it
I'm
is a
sorry.
good
I
time.
just
So
took a
that
lot
no,
of time.
no, it's not a problem. It's a really good thing for us that you got took that time for us, and we have discussed a lot of things. So thank you so much for making it possible, being with us, and I'm sure that we will continue making, and
Yes,
for
sure.
maybe
I hope so
in
too.
future we will have more discussions and more advanced level. So Dikshit sir is with us, so I would like to add him for some comments. Sir,
Uh,
we are about to finish. So, sir, some comments.
yeah. It's a very long session.
Yeah.
Though in parts I have to move here and there because of some administrative situations, but I found it in quite exhaustive, and Abhishek has done a marvelous presentation and make us to realize that how these two things, two aspects are coming together, and what is the convergence point, and how we can go ahead with all these ideas which we have studied in one way or the other at different levels, but that is their applications are absolutely tremendous in other fields. So I'm really very thankful to Dr. Abhishek for giving us a very long and exhaustive talk. I'm my students have also gets benefited probably. I'm quite sure. It might be that many situations is not their piece of cake, but स्टूडेंट्स के दिमाग में कोई चीज इम्प्लांट कर देना ज्यादा अच्छा होता है. धीरे धीरे वो उसको अपने आप से आगे बढ़ाते रहेंगे और इन चीजों को आगे ले जाएंगे, ऐसा मेरा पूरा विश्वास है. With these words, I am really thankful to both of you and to all my students and my colleagues who have discussed, who have witnessed this beautiful presentation. Thank you.
Thank you so much, sir. Thank you. Okay, so we are stopping the session. Thank you so much. Thank you.
Thank you. Bye.
God.